Another difference between electrons and matter in our everyday life is that electrons have equations known as wave equations because they take into consideration the wave characteristics of electrons that can accurately describe its behavior. We're going to look at the very tip of the iceberg of these wave equations, and we're going to look at three important numbers. These are integers known as quantum numbers that help describe the properties of an electron in an atom. The first one, the principal quantum number, often symbolized by the lowercase letter n, specifies the main energy level for an electron. And we've actually seen these quantum numbers in the hydrogen atom. These signified the energy levels that an electron could go to. And all atoms have these. These energy levels are often signified by these horizontal lines where electrons, just horizontal lines, and energy is increasing. Now what we're assuming is somewhere down here is the nucleus. The closer electrons are to the nucleus, the more stable they are. So our first energy level, those electrons are close to the nucleus. Second energy level, further away, etc. So as an electron gets higher and higher in its energy levels and further away from the nucleus, it becomes less stable. These energy levels also represent a general area around the nucleus. The area where electrons are that is closest to the nucleus is always the first energy level. The second energy level, further away, third and fourth, and as we go higher in numbers, our energy levels actually become closer and closer together, as we can see with our third and our fourth energy level. Now, in each principal energy level, remember that was these, 1, 2, 3, 4, there are subcategories known as subshells. And the number of subshells in a given energy level is equal to that principal quantum number. So let's look at how that works. If we look at our first energy level, our quantum number is 1, so there is one subshell in this energy level, or this shell. If we look at our second energy level, or our second shell, there are 2 subshells, because that's our quantum number. In the third energy level, there are 3 subshells. In our fourth energy level, there are 4 subshells. And what these subshells represent are smaller categories of energy levels. Subshells actually do have numbers, but in chemistry, we typically designate these subshells by letters, S, P, D, and F. The numbers, by the way, are 0, 1, 2, and 3, but the letters are what we'll be using. What these letters represent are 2 things. Each of these subshells has even further subcategories known as orbitals, and these orbitals have a particular shape. This shape represents the probability map, which, remember, is the 90% probability of finding an electron in that region. Another kind of astonishing fact about electrons is as they change energy levels, they change their shapes. Now remember, the shape that an electron takes is kind of like the shape that a fan blade takes. When a fan blade is moving, it takes on a kind of circular shape, solid shape. That's because it's moving so quickly. The same thing with an electron. Electron is moving so quickly, it takes on what looks like a solid shape. So we'll take a look at those shapes in just a second, but let's look at the subshells that are allowed in each shell. In the first shell, we have one subshell that is always the S subshell. In the second shell, we have 2 subshells that is always the S and the P. In the third shell, or third energy level, we always have 3 subshells, S, P, and D. And in the fourth shell, or fourth energy level, we always have 4 subshells. They are always S, P, D, and F. So our subshells are indicated by these letters, and then within our subshells are orbitals with a particular shape. So let's take a look at these orbitals. This is the S subshell. The S subshell always has one orbital, and it's a spherical shape orbital. So if we look back at our energy levels, we have an S subshell in every single energy level. And when we see that S subshell, it means there is one S orbital, and that S orbital has a spherical shape each time. Now let's look at the P orbitals in the P subshell. There are always 3 P orbitals in the P subshell, and they have this shape, kind of like a peanut. So we can remember S is sphere and P is peanut. And the difference between these 3 P orbitals is their orientation. The nucleus of the atom is going to be at the center of this Cartesian axis. One orbital is going to be oriented along the x-axis, the other, what we call the z-axis, and the other on the y-axis. So if we look at our second, third, and fourth energy level, they all have P subshells. This P subshell has 3 P orbitals, this P subshell has 3 P orbitals, and this P subshell has 3 P orbitals. Anytime we have a P subshell, there are always 3 P orbitals, and they are always 90 degrees apart, and they always have that same peanut shape. Once we get to the third energy level, we have D orbitals. When we have the D subshell, there are always 5 D orbitals. And 4 of them have very similar shapes. They look like a double peanut. And the only difference between these 4 is their orientation around the nucleus. And then the 5th one looks kind of like a P orbital, and it has a donut around the middle. So the third and fourth energy level have D subshells, and whenever you have a D subshell, you have 5 D orbitals. Same thing up here. We have 5 D orbitals. Here is the F subshell. There are 7 F orbitals, and they're very complicated. I refer to them F for flower because they have many, many lobes. So let's review. This is our S subshell, 1 S orbital. P subshell, 3 P orbitals. D subshell, 5 D orbitals, and F subshell, 7 F orbitals. Our first energy level only has the S subshell. Our second energy level has S and P subshell. Our third energy level has S, P, and D subshell, and our fourth energy level has S, P, D, and F subshell. And within each subshell are a certain number of orbitals. S always has 1 orbital. P always has 3, D always has 5, and F always has 7.